This presentation is about population dynamics with birth and death. Agent-based modeling of complex adaptive systems is all about populations in one form or another because we're looking at agents. We are examining populations of agents, their numbers, actions, and the resulting behavior that the population of agents we are modeling exhibits. What is a population? In general, a population is a group of living things, individual organisms of the same species living in the same place. Say ants living in a specific ant colony, or people living in a specific city, state, or country. In agent-based modeling, it is a group of agents. These agents can represent anything, those same ants, bees, or people. In this video, we are talking about modeling population dynamics of living things. Population dynamics is a branch of life science that talks about the characteristics of a given population in terms of its size, age, reproduction, and death. Population dynamics not only studies the characteristics of a population, but the changes of that population. Population dynamics, or population change, is only affected by four things. Two cause the population to increase: birth and immigration. Immigration is when creatures, or the agents, move into an area. And two things cause populations to decrease: death or emigration, when creatures or agents move out of an area. So if you're looking at the population of fish in a lake, the things that affect the population are the things that affect the birth and death of fish, such as infection, pollution, predators, and how the fish move into and out of that lake, say through streams, rivers, or perhaps by stocking of that lake. In this video, we're going to focus on birth and death. Things that give you positive feedback are things that enhance whatever you're looking at. It's sort of like good things give you more good things. In the schematic below, if you start with some rabbits, and they have all the food they need and nothing eats them and nothing kills them, then you'll just get bunnies. And eventually the bunnies will lead to more rabbits as they age, and that will lead to even more bunnies. The number gets bigger and bigger. Not only does the number get bigger and bigger, but it gets bigger and bigger, faster and faster. Why? Well, let's think about it. If you start with a rabbit, and it has two babies, then each of these two babies eventually become rabbits, and they go on to have, say, two babies apiece. So then you end up with 4 rabbits. If those 4 rabbits have 2 babies apiece, then the next time around, you get 8 rabbits. So each time you go through the cycle, you get more and more rabbits. This type of growth is called exponential growth and is shown in the simple graph to the right. You can see the rate at which the population of rabbits is growing increases faster and faster. Now, in the real world, something always interferes with this process. Otherwise, the world would be covered with rabbits. And that something is called negative feedback. Negative feedback occurs when things slow down or decrease whatever you're looking at. So in the case of the rabbit population, negative feedback would be anything that caused rabbits to die or slow down the birth rate of rabbits. And this can occur any time during the whole rabbit population cycle, not just where the arrows are. Some things that might cause negative feedback in this rabbit population loop would be predators, or perhaps you have too many rabbits and they're competing for food, or too few rabbits and the rabbits can't find mates. Perhaps the rabbits have some sort of health problem. They have diseases or illnesses, or perhaps there's just not enough food to go around. All these things cause rabbits to die or slow down the birth rate. Therefore, they would be negative feedback. So how does negative feedback affect that exponential growth curve we saw before? Well, it limits the growth of population. Sometimes an upper limit in population occurs, as shown on the left. This is called a logistic graph. More often, the population will fluctuate, as shown on the right, which is a cyclical graph. So how do you model population dynamics? Well, if you were creating a very detailed model of population dynamics, you would include all the things that affect the birth rate. For instance, the health of the rabbits, the health of the population, how much food is available to the population, and if there are enough mates for the population. And you would include all the things that affect the death of the population, which also include health, food, population, and of course, predators. Now in a simpler model, you would incorporate all those effects into a single birth rate and a single death rate. And that's what we're going to accomplish in the modeling that we do. So how would you model birth? There are many ways to model birth. You might model birth as the interaction of agents of the same breed, such as males and females in a population. So you might say, anytime a male and a female in the population interact with one another, there's a certain probability that interaction will result in a birth. Or an agent-environment type of interaction. Say, for instance, a location. Maybe the species can only give birth in a den. Or say if they have the right type of food. Or you could model birth based on the changes in the specific agent. For instance, maybe it has to reach a certain age or have a certain amount of energy. That's how we're going to start modeling birth. We're going to say when each individual agent's energy is above the birth threshold energy, then there's a certain chance that birth will occur. And once birth occurs, energy is lost in that process. Here's how it might look in the model. You would ask the turtles to do a bunch of things, I'm sure, and then you would say, if energy is greater than the birth threshold energy, set the energy to be the energy minus the amount of energy you lose during birth. Hatch however many babies you want to, and move them all forward one. Otherwise, they'll be sitting right on top of their mother. Similarly, there are many ways to model death. Again, agent interactions could result in death, for instance, a predator-prey interaction, or perhaps your agent encounters an infected agent and dies because it's infected by some disease. Also, agent-environment interactions could result in death. Perhaps some location on your net-logo plane is deadly. Maybe there's a cliff. Or maybe there are toxins in the environment. Walks over that toxin, it dies. Or again, maybe changes in the agent itself. For instance, if the agent becomes too old, maybe it dies, or gets a disease, or maybe it doesn't have enough energy to live. That's how we usually start modeling death. So if the agent's energy is less than the death threshold energy, then the agent would die. Here's how it might look in the model. You'd ask the turtles to do lots and lots of things, I'm sure, and then if the energy of the turtle is less than the death threshold energy, then the turtle will die. Let's go take a look at a model. Here we are at the wolf-sheep predation model. Let's go look at the code. You can see that we have two breeds, sheep and wolves, and each turtle, that means all the sheep and all the wolves, have an energy. And when we create the sheep, we set the energy to be some value. That's really important because if, say, for instance, you didn't set the initial value of the variable energy to be something other than 0, and your death threshold was 0, then right away all your agents would die. Let's go look at the birth and death of the sheep and wolves. Here we have the birth of sheep. Now we're saying if the value of some random number is less than the sheep reproduction rate, then we're going to set the energy to be half of the energy it was. So every time the sheep reproduces, it loses half of its energy. And then we're going to hatch one sheep and move it forward. We're going to do something similar for the wolves. Here we see that if the energy is less than 0, then whatever the turtle is, it dies. Let's go take a look. There we are. We see that the net logo plane is scattered with sheep and wolves. Okay, we've turned the grass on in the model. That means that the grass is also another species. Let's take a look. Now we can see when we look at the graph that after a while, the sheep and wolf population shown by the blue and red lines just keep oscillating back and forth. So we get a cyclical population of agents. In summary, a population is a group of living things. Population dynamics is the study of the characteristics and changes in a population. Positive feedback results in an increase in the population, and negative feedback results in a decrease. Some types of population growth include exponential, logistic, and cyclical. And you can model birth and death using agent-agent interactions, agent-environment interactions, or changes in the agent itself. Thank you.